Okay, previously in our module 5, we look into process scheduling. There will be several things last time we take a look into, especially for the burst time, and then when you also play around with the job and process status. Over here also you learn on scheduling, and we have several exercise which is related to dispatcher. So we have like 2 or 3 exercise. We done it together. So I hope that all of you did try again. Maybe you can change the value and try to draw your own diagram. So that is very important, how you're going to draw. And in terms of the requirements, it's depend on the question like this one. So there is a special requirement for each question. What else? We take a look also in terms of several algorithm, especially when we want to find out the value of turnaround time and waiting time. Especially lastly, you're going to find the average of turnaround time and average of waiting time. So I hope you still remember there is several algorithm like first come first serve, FCFS, short job or first scheduling, SJF, or it can be called also as SJN. Okay, SJN or SJF. After that, you have what else here? You have a round robin. So these 3 algorithm we already discussed last time. So today we're going to look into parity scheduling and lastly multi-level queue scheduling. Before you go deeper for next algorithm, you need to remember how to do FCFS and RR. This is mostly like hot algorithm because it also needed to be applied when you do multi-level queue scheduling. Okay, so if you still don't know, it's hard for you to move around. Under FCFS, we also already tried to look into how to draw the Gantt chart illustration here, how to calculate the waiting time, how to calculate the average, which one is the turnaround, and etc. So it is basically similar. Normally, waiting time normally waiting time is the time how long you need to take for each process, whether it is process P1, P2 or P3. How long they need to wait, to start their process. Okay, to start their process. Let's say for P1, it start directly at 0. So no need for you to wait. That's why the waiting time is 0. And then you look into P2. P2, when it start? 24. So this is while waiting. You can see while waiting. This is all the time for P2 to wait it to start. So that will be a waiting time for P2. And along all of this, P3 is waiting to start. So it start at 27. So that's why the waiting time will be 27. Which is vice versa from turnaround time. Turnaround is mostly like when it's finished the process. For P3, you can see the turnaround time is finished at 30. P2 at 27, P1 at 24. So here is turnaround, here is waiting time. So I think that all of you already familiar because there is a lot of example we've been discussed together. And that is on FCFS. After that, we take a look into, of course, the advantages and disadvantages for FCFS. And short job first, SJF, SJN. There is also several example and similar also the disadvantages and advantages. Okay, this one is under SRT, SRTF. We also been discussed last time here. And lastly, on the round robin, which is, I think, last time I mentioned round robin is like much more easier compared to the first come first serve. But first come first serve also, I think it's easier. So you can see these two easy methods are always been chosen to be used. So round robin trigger or effect, you need to look into the time quantum size. So you were given with the past time and you need to look into the quantum. So that is under round robin. And now we going to start with our new algorithm. I hope that all of you already familiar, okay, with previous algorithm. So now we're going to look into time quantum and context switch time. So here you're going to also apply the RR algorithm, round robin. And round robin, you know that there will be play around with the time quantum. And that's why, let's say in this example, it gives you several quantum size. First, let's say this one is like a process 1. For process 1 here, you were given P2, P3. The process duration is 10. Similar. We assume it's to be 10 millisecond. And you have each quantum. For process 1, the quantum is 12. Means that your process can finish before the quantum. So let's say you reach 12. You can see before 12, you already finish your process. So there is no context switches. While if you have the quantum 6 at 6 millisecond, you have one quantum. Let's say until 12, you have another quantum. 18, you have another quantum. But you can see here, you just want to check until 10 millisecond. So that's why in this range, you have only one context switch that occur depending on the quantum. So 1. So in the range of 0 to 10 here, from 0 to 10, how many quantum that you can have? Okay, the quantum is 1. So every 1 millisecond, it will occur the quantum. So there is a context switch 1, 2, 3, 4, 5 until 9 here. This is all the context switch that available from 0 to 10. So this is just example for you to understand and relate between time quantum and context switch time. Here is a turnaround time varies with the time quantum. So just example, when you have the time quantum, when you have the average time, turnaround time, but this one is need to depend on the scenario, but it's not clear in the example here. But just to show you that you're going to have different turnaround time if you have the different time quantum also. So maybe you can try to draw if you have a P1, how long you have, but it doesn't mention that the time quantum. Okay, it's depend on how many time quantum that you have. So if you have 1, so how it's going to be look like? So you need to try to do until 7 time quantum for all this process. So you can try to draw and look into, you're going to get different value of your average turnaround time. Okay, let's see the example here. We have job A, B, this one is after that, okay. First of all, we look into example A. It mentioned that time quantum is 10. So you need to assume like until here it's going to be 10 millisecond. So time quantum as 10. In job A, which require only 8 cycle to run, or might be, sorry, 10 might be until here. 1, 2, 3, 4, 6, 7, 8, 9. Okay. 10 until here. Okay. Okay, you can see, let's say we start similar, which is at T0. So for T0, let's say for job A, it have the time, or might be normally you look into a CPU burst time is 8 cycle. So you have a CPU for job A is 8 cycle. So the time quantum given is 10. So you finish before it, before the job A. Okay, before the quantum, job A is finished. While finish before the time quantum expired at 10. And then you have a second one. Second one, the time quantum is 5. And job A. So supposedly, let's say you have example for job A still similar, which is 8. But your time quantum is already 5, isn't it? Job A, 8. B, I don't know, maybe we assume like 5. C, 3, whatever value. But the thing is you're going to see here. Okay, job A, supposedly it's going to finish until 8, isn't it? But when you have the time quantum, remember back your round robin, when you have a quantum, if the value is 5, so you're going to minus 5, you have the balance of 3. So until here only. So your job A is not yet finished because you have another 3. It will continue with another job. So might be job B is 5, so finish until 5, another quantum. Then, let's say we don't have any job C, it will continue back the job A. Job A, which is 3. Although the time quantum is 5, but we have only 3 left, so we just finish until 3. Okay, next we have example C. The time quantum is 1. So it depends whether you have job A equal to just now like 8 cycle. But when you have 1 here, so you're going to stop at 1. It will continue later on after the other's job is finished. So let's say until K, you have until K job. So your job A will continue here. If you have like 8 cycle, there is another 7. So here 7, but you only have 1 quantum. So you need to continue later on another one. It depends on how many jobs that available and left after that, isn't it? So just to see, example B and C, the time quantum expired first. So you can see it expired first before the job is finished. So it's going to interrupt the job. Okay, here for case A just now, for case A just now, there is no context switch. Why? Because you finish earlier. You finish earlier before the time quantum expired. That's why there is no context switch. Similar also in the passive example here. So job A run the completion since CPU burst and shortly before time quantum expired. No difference between RR and FCFS policies if you apply at a example or case E. For case B, there is one context switch for the rest of job A. Job A is preempted once when the time quantum expired. And lastly, for job case C, there is 10 switches contact for second cycle of job A, because job A will be continue after that. The job is preempted every time the time quantum expired. So you can see here there is a weakness for the case B and C, which is there is overhead that might be become a costly, and turnaround time suffering. That is your turnaround time, I guess, might be huge compared to case A. Okay, parity scheduling. Let's see on the parity scheduling. Sorry, I need to unmute because I also got fever. Flu. The fever is like already finished yesterday, I guess, but still continue flu and a small cough, I guess. Okay, let's see what we have here for our parity scheduling. A parity number, which is integer, is associated with each process. The CPU is allocated for process with higher parity, and smallest integer is the highest parity. So let's say you're going to have highest parity and low parity. So you have two queue. But later on, you're going to look into these queuing things later on in your multi-level queue, especially when you have a foreground, background. Okay, but now it's just to inform you that the smallest integer having the highest parity for the CPU allocation to find out which one is the highest. So preemptive and non-preemptive. I think for the smallest integer, this one you already know. That smallest, you're going to tag it first to run the process. SJF or SJN is parity scheduling when the parity is the inverse of the predicted for next CPU burst time. So what is the problem that might occur, which is starving? Which is low parity process may never execute because of there is like long on waiting. So that's why you need to have another solution for this starvation problem, which is edging. This edging later on you're going to look into, which is you wait too long, so you will like push from low parity to high parity. Let's say you have job 1, job 2. Your job 2 is low parity. Job 1 is already sent to your CPU. And then there is another job coming in. But you can see your job 1 is already run and CPU know, okay, after this I'm going to hands-on to job 2. But suddenly there is job 3 coming in. Job 2 is already waiting too long. This problem. So using the methods of solution edging, so job 2 will be pushed to higher priority later on. Then coming out for job 3. So later on you're going to look into how this edging solution can solve the problem of starvations as the time process increase the priority of the process, which is from low priority to higher priority. Okay, let's see example 1 here. You were given with 5 altogether, 5 process and their burst time. You already been given in the priority. Priority, which one is the first one, second one, third one, and so on. So you need to follow the priority under priority scheduling. Okay, which one is the priority higher? Which is P2. Which one is the second priority? P5. You can see here, although last time you will took into the bus time. If the bus time is smallest, you're going to take first, isn't it? But now you're going to only look into the priority. So we have the P2 first. So P2 will be here. P2, how long you have? 1. And then second one is P5. You can see here P5 and you have the bus time is 5. Third one is P1. So you have a P1 here. And altogether you're going to see you have 10. Supposedly 16. From 6 to 16. I think there is a numbers missing here also. Let's take a look first what happened. After this, we're going to have 4. 4 will be P3. P3 will be another 2. And lastly, we have 5, which is 19, which our P4. So how you going to measure? How you going to measure the average waiting time? So the waiting time for P1 will be 0. For P5 will be 1. We have what after this? Third, 6. And then P3 will be 10, 16. And lastly, 17. Tadi I buat sampai 19 salah Wait This one is 6, 16. After that, P3 we have 2. Okay, sorry. 16. And P4 will be 19. 6 at here. P3 is 16. P4 is 18. So this is average waiting time. Can you try to calculate how much you're going to get here? Calculate with calculator. Did you get the similar one?
Yes.
What was that?
Yes. 41 divided by 5. Yes.
Okay, 41 divided by 5, you're going to get 8.2 milliseconds. So this is average waiting time for the calculation. So please make sure you know how to do the Gantt chart. This one we already learned together last time. And how about the turnaround time? Okay, the turnaround time is when the job is finished. This is also important for you to know how to calculate average turnaround time. TT, which is for P4, we have, alamak, tadi berapa? 19. 19. For I start from here first. P2 is 1. P5 is 6. P1, 16.
16 and then P3 is 18.
18 here.
18.
So after that, you're going to add it all together. And you divide with 5. You're going to get the turnaround time. Okay, so these two questions will be like a favorite question for all algorithm. Okay, so please make sure you know how to calculate it. But when you have another, like let's say you have P2 is not yet finished, especially when you have the quantum. So P2 having also here. So your waiting time and turnaround time will be different. You cannot just directly look into like right up above here and left below here. Okay, so you need to calculate it carefully. Later on, we have also example like that. Previously, we do it together also. Let's see after this, okay? So continue. Wait. Okay, system administrator or Ya Allah, tertekan. Okay. System administrator or process manager use different method of assigning priority. So process manager priority assignment method having 4 method. Memory requirement, you can try to check it. Numbers and type of peripheral device. Total CPU time, amount, time already spent in system. Normally, this kind of question will be coming out in terms of your MCQ. You need to memorize the methods, But normally in like this example or exercise, you need to do drawing and also calculation. Okay, for this exercise 3, you have 5 also. 1, 2, 3, 4, 5. 5 process, which is arrive at time 0 all together. With the CPU different, burst time, and parity level. So, under a parity scheduling algorithm, you going to see okay, you have 3 things that you need to do. Okay, so might be you can try to do it FCFS, SJN, and you're going to look into which one is the best. But how you're going to define it? For parity, of course, you're going to draw just now like this one is first, job B, and then number 2, job E, 3 is job A, 4 is job C, and lastly job 1, 2, 3, 4 job D. So here 0, job B will be 1, job E 6, job A 16. Sama ke? Job C 18 and 19. Oh, similar one. So here, from here you calculate, which of course you're going to get similar in the question here, but try to also apply the FCFS SJN. How about the average waiting time and turnaround time, and why it is the best? Let's see here on in terms of the combining parity scheduling and also round robin. System execute the highest parity process. Process with the same parity will be run using round robin. So it's already mentioned, okay? The same priority will run using round robin. Round robin, you still remember that you need to see the burst time. Which one is the smallest? It's going to start first. So you can see here in the parity, you have 2 similar parity. So for this and this, you're going to do using round robin. For here priority 3, this also will be doing a round robin. What else we have? So let's see one by one. For the priority 1, there is no same priority. So that's why we can directly tag this. We can directly tag this to be first process. So here our P4 will be doing first. So here our P4 will be doing first, and it's all together. The burst time is 7. 0 until 7. After that, you can see you are having 2 and 2 here. 2 and 2, which is you going to do the round robin. So maybe you can try to look back the round robin, how to do the round robin. So supposedly there will be a time quantum for you to look into. In this question, it's not mentioned, but in the test, final exam, it will inform you. Okay, but looking at the example, you can know how much the quantum size is taken for the example. So let's see here. Okay, here. So these two, which one going to do first? So you're going to do the P2 first because this is the smallest on the bus time. But you can see you have 5 here. But from here in the example, you only have 2. Means that supposedly it means there will be a quantum equal to 2. Let's check here whether it's correct or not. So you have minus 2, you have another 3. Remember? So first time you're going to have 2, you have 3 left for P2. So you start here, only 2. Similar also, when you have the quantum in the equation, it will inform quantum 2, it will be applied all. Okay, it will be applied all for the round robin. So here, you will continue with the P3. Because this is similar priority, you're going to take the smallest first time first. And you're going to continue with the P3. From here, round robin, is it first time? I guess it is also depend on the which one is coming in first. Okay, you can see that's why is first come first serve, but round robin will be looking into the quantum and the burst time. Okay, after we finish, we're going to start with P3. So this is our P3 here. For P3, you can see the size is also 2. So P3 minus 2 equal to 6. There is another 6 here for P3. But just now, for P2 is having left 3. So you're going to continue these two together until they finish because you're going to finish the priority 2 first. Priority 2. Continue here with the process of P2, another 2. Continue. Minus 2 equal to 1. Another 2. Minus 2 equal to 4. So you continue with the P2 here is only 1 left because only 1 here left. So this is 1 only. Then you have nothing for P2. That's why you're going to directly, although you can see you have left 4. So you're going to finish all together for P3. This one is the total of 4. So you're done at the priority level 2. So here you're going to take a look into the priority 3. For the burst time is 4 and 3 here. This one is the earliest coming in. The priority is depend which one is coming in also. So P1 will be the process, but still remember the quantum which is 2. So it's going to be 2 here, minus 2, minus 2. You're going to have another 2 here. Left equal to 1, left equal to 2. This one is 2 and this one is 1. So from here, you can see how you're going to measure. Kenapa tak boleh delete? Okay. How you're going to measure the average waiting time and also average turnaround time. look into one by one. So P4, the waiting time is 0 because it's directly start. And for P2, you have several. You can see here, you need to wait until 7 seconds. P2, okay. 7 seconds, you start. But then you can see you need to wait another one. Another 2 seconds, you're going to wait. The second one, you're going to wait another 2 seconds. Alhamdulillah, sorry. And you can see also you need to wait another 2 seconds to start a P2. Then there is no P2. So this is all waiting time that you need. But you can see last time we learned how you're going to calculate waiting time also in terms of deductions of 16 minus 15 and then 13 minus 11, 9 minus 7, 7 minus 0. You look into that, the example last time. Then you can find out the average waiting time. And also similar also for the turnaround. Turnaround time also you need to take a look into when it finished. For P2 when it's finished, P1 when it's finished, P4 when it's finished, and then you're going to average it. Now we will look into the multi-level queue. This is the last algorithm, but you can see although this is another new algorithm, but you still need to apply the round robin and also FCFS, first come first serve and round robin. So you in the multi-level queue, you need to separate into several queue, and mostly we have 2 queue at least, higher priority and also lower priority. 2 queue, Q1, Q2, means that this is the lowest queue. Is need to wait for highest priority to send and run at the CPU first. And normally, foreground is the interactive one, background is the bash, and this multi-level queue will always apply at the hybrid environment. And when you apply the foreground, you're going to use the RR for background, which is FCFS. Let's take a look into the example. Okay, this one, this is not a clear example. This one is just for you to have several priority. Okay, which one will we go for the CPU first? After that, it continue for the priority and etc. So let's take a look into example. You have several cases, which is 4 methods altogether. When you apply the queuing. First case, when there is no movement between queue. Second case, you have a movement between queue. What is the difference? Which movement that will be occur in the queuing? And case 3, time quantum per queue and edging. Edging also going to apply the movement between queue, because last time, if you still remember, edging having a movement from lower parity to higher parity. Okay, for the case 1, no movement. It is the simplest method. This is all the advantages. And let's see how no movement between queue. In the question, you will directly inform if you have arrival of job at T0, similar time, all together coming in. it will inform you which one is higher priority, which one is the lower priority. So in the example, we give like job 2, job 3 is higher priority, and lower priority is job 1, job 4, job 5. So we're going to apply the FCFS. Which come first is going to be served first. So let's say J2 is coming first. So it will, you can see here, J2 is coming first. So this one will be sent to the CPU to process first. This one waiting for J2 is finished. This is waiting for higher priority to finish. Okay, J3 waiting for J2 to finish, while J1, J4, J5 waiting higher priority to finish. So after dia tak gerak. So after that, J2, after J2 finish, then J3, then all higher priority is finished. Now the tech turns is the lower priority, J1, J4, lastly J5. This no movement between Q means that J1 not going to go to the higher priority. J4 also, there is no movement from lower priority to higher priority, or from higher priority there is no movement that going to go to the lower priority. After this, you're going to see when you have a movement, you can move J2 to lower priority. Okay. So here is the case 2, which is movement between queue. Process adjust priority assigned to each job, and higher priority's job initial priority favor treat like others job afterward. And this is the most important when you have the quantum interrupt. That will be happen the movement because you have quantum. That's why you're going to move to the next lower queue. Just now you have example high and lower only, right? Higher and low, that's why you move to second one. If you have another very low, so from low you can go to the very low, which is the next lower queue. May have priority increase also, which is might be you can go from lower to the highest. Good environment job handled by cycle characteristics, CPU or input-output interactive system. Okay, now let's take a look into the example for movement between queue. And you can see here, just now I inform you, quantum interrupt having for the case 2 movement between queue. Means you can see there is a time quantum. But it is for the higher priority. There is no time quantum at the low priority. But it's okay. It's depend also on the question. You need to know the basic on the movement between queue. We use the similar example, which is job 2, job 3 having the higher priority, job 1, job 4, job 5 lower priority, and we give the CPU burst. When we have CPU burst, we have the quantum time. Of course, there will be a limitation. We cannot finish the job if the time quantum is already occurred. So first of all, you know that this J2 will be take place. But you can see here, CPU burst is 10. But the time quantum that you can finish this job, like you're going to do the job 2. 0 until 5. Why 5? Because the quantum is 5. You have another 5, job 2. So you're going to continue with what? Job 3. But still remember this one is the job 3, and then job 3 having a job 3 is what? 4. So you're going to have 9 like this. After that, you're going to continue with job 1, job 4, job 5. Why like this? Why you did not do job 2 directly here? Because on the movement between Q, job 2 will be pushed at the lowest parity. So it's not yet assumed to be here anymore. That's why it's not started at here. So here will be job 1, job 4, job 5. After finish, then it will take the job 2 back. Okay, so this is the things that we always see in terms of this Gantt chart. But in terms of the movement, job 2 will be doing first. And you can see here, you have the balance of 5. And you will push it, go to the lower priority. Move to the lower priority or lower queue. That's why you move it here. Okay, move it here, not in front here. So when you already move here, you're going to still focus on the higher. So higher is 3. It is under 5. So it can finish. Finish all together. Job 1 will be finished. Job 4 will be finished. Job 5 will be finished. Then continue lastly the job 2. Because job 2 just now have a balance. So finish this job 3 first. After that, job 1, job 4, job 5, and lastly the job 2 again. So this is under a movement between Q. When you have the time quantum and you're going to move from higher parity, you already go to the CPU, and because of the time quantum already meet, you're going to move it to the lower priority. Next, we have case 3, variable time quantum per Q, which is a variations of movement between Q. You can see there is a movement between Q, whether it is higher priority or lower priority. Each Q given time quantum size. So you can see here just now, in the previous example, you have 1. But now for variables time quantum per Q, means every Q have their own time quantum. And there is also TNC for the time quantum, which is size twice as long as previous Q. Let's say for our higher, lower. For higher, we have the quantum equal to 4. For this stated of statement, twice mean double. For quantum for low, it will be times 2 equal to 8. Quantum, okay? So lower will be 8. Fast turnaround for CPU bound job. CPU execute longer and given longer time period, which is improve the chances of finish faster. Okay, let's take a look into the example. Again, you can see here at the higher priority, At the higher priority, the quantum is 5, and mentioned here it is twice, means it's double for the next queue. That's why you have 10 at the lowest priority for the variable time quantum per queue. So you were given also CPU burst time here. Let's see what happened. Time quantum 5. J2, we have 15. So we have 15. It is not enough, right? So when you have job 2 first here, you have another 10. You have another 10. So you're going to move it to the lower priority. Lower priority, and then job 3 is enough for 4. Okay, let's take a look into the movement. So job 2 will be having balance of 10. Which one will be took first? Of course, the higher priority, which is job 3. Continue with job 1, job 4, job 5, and lastly job 2. So the most important you can see here for a variable time quantum per queue is having the per queue having their own time quantum. For the movement, there is no, for each queue there is no time, only one at the higher priority might be, so you can see the time quantum. But for per queue, all the queue are having, but it will be double. And last algorithm, last method, sorry, edging. For edging, giving a special treatment to job. Just now we look into when you are having a problem with the starvation. That's why you need an edging method to solve the problem. To ensure lower level Q job eventually complete education, system keep track of job wait time. If to all, system move job to next higher queue. This is the things I mentioned, from lower to higher, because you already wait too long. Continue until all job reach to the top queue. May drastically move all job to higher queue. So this is the advantages. Let's take a look into the example. The scenario slightly different from previous 3 example because your arrival job is at different time. Firstly, you're going to have job 1, job 2 at the arrival of T0. So job 2 will be the highest priority if you still remember. Job 2, similar example, is higher priority. Job 2 having CPU burst with 100. So you will move here to the CPU. It will do 100 CPU burst, which is job 2 is running. CPU will notice, okay, after this, which job will be taking place. Of course, CPU will plan before it's going to hand off, isn't it? So the queuing, you can see only job 1 are waiting. So it know, okay, job 1 will waiting and will take place. But while waiting, suddenly, while waiting at T50, a new job arrived. It's mentioned the lower priority for both. And job 2 is still running because not yet finished. It is 100. So it will be moving J3 here, J4 here. So here you can see Suddenly, while J1 waiting, it's too long now, too long for waiting to J2 to finish, and then at T70, job 5 is arrived, and you know it's higher priority, so higher priority you're going to put here. J2 is still running. J1 has waiting 70 CPU burst time already. Waiting too long already. Supposedly you're going to say, okay, this one is higher priority. After J2 is finished, J5 will be taking place. But before it will be placed here at the higher priority, it will see that J1 is already waiting too long. So that's why under edging method, it will push this J1 because it's waiting too long to the higher priority, because you know after this it should be this one that need to run. Similar also when you wait for some like food at the bazaar, of course the seller will notice, okay, after this who going to get, although there is a VVIP coming in, because it is a VVIP higher priority you're going to give, but you know there is someone that waiting too long. That's why you're going to say, okay, I'm not going to give to the VVIP first because it is too long. If not, it's going to scold you, right? So that's why you're going to move the J1 to the higher priority. Then you're going to ask, okay, VVIP, after this, I'm going to give you. You are at the higher priority, although there is another customer waiting. But you know, okay, they're not waiting too long, like what J1 are waiting. Okay, so here J1 is already at the higher priority, and it will take place after J2, J5, and continue with others. So this will be J2 complete, J5 then running, continue with the lower priority job. Here is the summary of all the methods that you already looked into: FCFS, SJN, priority scheduling, SRT, round robin, multi-level queue. So please make sure you try to look into this summarized table. For multi-level feedback queue, a process can move between a various queue. Edging can be implemented this way. Okay, just now you look into the edging method. The idea is to separate process according to the characteristic of the CPU burst. So multi-level feedback queue scheduler defined by the following parameters: number of queue, scheduling algorithms. You have a lot of scheduling algorithm for each queue. Method used to determine when to upgrade a process, when you're going to demote a process, and determine which queue a process will enter when the process need a service. So here is a similar things, which is similar example when you have 3. Just now we look into only 2 queue. We have 3 queue here, Q0, Q1, Q2. So you're going to apply RR for our Q0 and Q1, and lastly for last Q going to be FCFS. From here, if your quantum is 8 and you are having like might be job A equal to 10, if you still not yet finish, you're going to move to lower Q. If still not yet finished, you're going to move to the lower queue. It is similar also with the previous one, which is you're going to move to the lower queue. Similar also example. Only for this example here, you have three queues. So you can see how much you move to another. Okay, let's see exercise 4. We nearly to end. Let's see the exercise first. You have 5 altogether, but you were given with the different CPU bus and also priority. There is no similar priority, but it's mentioned about assume that MFQ scheduling algorithm is applied with 2 levels and the priority range of 1 highest. So given an initial time quantum for the first level is 5, so it's already give you 5 CPU burst, and the last level using FCFS, so last one will be job D. Calculate the average waiting and turnaround time. So let's see and how we're going to draw. First, this is our first priority, which is job B. Job B will be coming first. Will be doing first because this is the highest priority and it's have 1. Second is job E. Job E having the CPU bus is 5. And then job A is 10. That's why later on you're going to see our bus, our quantum is 5. So you're going to move to another queue. Okay, after this, okay? But this one is just for you to do the queuing first. The fourth is job C. And lastly, our job D. This one is how you're going to queue to the CPU, supposedly. But you have the quantum, of course, this one will be trigger something. You're going to move it to the lower queue. So now we have Q0, first queue. The quantum is 5. So first we have job B, total of 1. Then job E. Job E, total of 5. Job A. What happened to job A? You supposedly have 10, but cannot because your quantum is 5. So you can only do 5 here. Minus 5, you have another 5. This one, what happened? You're going to move to another queue. Q1, which is lower queue for job A. Okay, but waiting here only first. Then we're going to have job C. Job C, 2. And lastly, job D, 1. After finish here, then you're going to continue with another queue, which is job A. Left equal to 5. Starting at 15 until 20. So this is how it's look like when you try to do. Basically, it is a continuous, but you just need to know that when you're having a several queue, you have another queue created. And how to calculate the turnaround time and also waiting time. So waiting time, as mentioned, waiting time for job B. Job B will be finished directly. It doesn't have any waiting time directly. So you have 0 here. For job E, waiting time is 1. Job E, waiting time having 2, so we ignore first. Job C, waiting time is 11. Job D, waiting time is 13. So go back to the waiting time for job A. For job A, you can see here, this is the waiting time. How long you're going to have? 6. But you have another waiting time. From 11 until you start at 15 here. 15 to 11, you have 4. So altogether, you have 6 plus 4 waiting time for job A to start. So you're going to have 10. That is on the waiting time. Waiting time is easier. So you can add on and divide with 5. While for turnaround is like a completion of the task. So for job B, it's complete at 1. Job E is complete at 6. Job A, okay, later on. Job C is complete at 13. And job D is complete at 14. Now here you can see you are having job A here. This is not your turnaround time because you have another one at this part. This is the completion time or your turnaround time at 20. So you add all together, divide with 5. This is how you're going to measure the average waiting time and turnaround time. Similar with another example previously we looked into, although we are using a FCFS, round robin, SJN, all need to use a similar things in terms of turnaround and waiting time. Okay, any question for this example? So you can also see lastly we have the summarization for all throughout our module 5. Processor manager allocates CPU among all user. Job scheduler assign job to ready queue based on characteristic. Process scheduler instant by instant allocation of CPU. Scheduling algorithm is unique. And lastly, system designer select best policy and algorithm. So that is the only things that cover for your module 5. Alhamdulillah. Okay, any question? So I think if there is no question, you can look back this video recording. Where's your... Okay, wait. Okay, you can look back this video recording. I will upload to the YouTube and share to your e-learning. And for those who still not yet scan QR code, please scan. And we will continue our module 6 next week. But please make sure, remember that you have your task to do your lab 2. I already create the lab 2 submission. And the due date, I remind again, is 15 May. So please make sure you submit on time. Submit it individually, although it is similar with your group member. You need to do with your team member. Your answer is similar, your video is similar, but please submit it individually, okay? So thank you, class. We meet again next week on Sunday. Bye-bye. Take care. Assalamualaikum.
Thank you, Doctor.
Okay.
Thank you, doctor.
Thank you.
Thank you, doctor.
Thank you.
Doctor, so meaning that every person have to take their own video. Is that correct?
Wait, because I can't hear you. Okay, again?
So when you say the lab must be submit individually, so does it mean everybody have to make shoot their own video?
No, no, no. Similar video with your teammate, but submit individually.
So it means that we can share our video with our teammate. Just make sure the submission is done for every person.
Yeah.
Oh, okay, okay, understood.
Okay.